So, what is equilibriums? So, basically, equilibriums is occurs when opposing force or action are balanced. So, we can take example of tug of wars. Tug of war is static equilibriums is basically no motions. So, we can assume that tug of war got a balance force both of sides. So if there's both sides of same balance of force, there's no motions going on. So for the chemical equilibrium, it's more into dynamics. It's basically constant motions. Alright. The next thing is we can take example of tap water. It's running constantly. So basically, a chemical equilibrium occurs when the forward and reverse reaction rate are equals. So for number one, reactant react to form products. For number two, product react to form reactants. So for number three, amount of each chemical stays the same. Alright, we got some example here. So H2 plus Ln2, we're gonna get 2 HNOs. So basically, the reactions do not stop when equilibrium is reached. So basically, what you do here is constant motions going forward and reverse. So it's basically a constant motions going on right now. Alright, let's go to the next step is so basically there is a three characteristics of our system in equilibriums. Alright, so for number one, closed system. For number two, the rate of the forward and reverse reaction are equals. For number three, properties such as concentrations of reactants and products. Colors are constants. So that means is basically if we do some equations, we're gonna get the same color. So that's why we're gonna get color are constants. So what is K stand for? Basically, if K more than 1, reaction is product favor. If K less than 1, reaction is reactant favor. Alright. So what is C in Kc stand for? So basically C is indicates the concentration unit of the reactant and the products. Alright, let's go to the next step is equilibrium constant, Kc. So basically Kc is the ratio of the equilibrium's concentration of product. So we can take an example of this formula right here on the slide. Right. So for the next step is equilibrium constant in terms of pressure Kp. So reaction involving gas, the equilibrium constant is often expressed in terms of the partial pressure of the gas. So basically, if it involving gas, it's basically equilibrium constant. It's given to Kp. Right. So there's example right there, and formula we can use for involving gas Kp. Alright, let's go to the next step is the reaction coefficient QC. So basically, reaction coefficient QC is a mass action expression just like the equilibrium constant LC, except it is for reaction at conditions, not at equilibriums. So that the reaction coefficient is used to determine which direction a system will shift to reach equilibriums. Alright, so for examples, we can use this formula. So it's basically where A, B, C, and D are molarity at any times. Because it's basically going forward and reverse. That's why it's our molarities at any times. Alright. So the last thing is comparison of Kc and Qc. So basically Q equal to K, number one is the system is already at equilibriums. For number two, it will not shift in either direction. Alright, Q more than K. For number one, the system will shift to the left. Two, some product will convert to reactants. Q less than K, the system will shift to the right. Number two, some reaction will be converted to products. Alright, that's all for me. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ziad bin Muhammad Zaini and my student ID is 2025873922, and in this segment I'm going to show to you guys how to calculate Kc, Kp and Qc in chemical equilibrium. So let's get started. So for example, let's take a look at the reactant and the product, which is the reactant is 2SO2 plus O2 and forms into 2SO3, which is the product. And at 700 K, the equilibrium constant Kc is 4 times 10 power of 4. So for example, for question A is calculate Kp for the reaction. So in this question, we're going to use a formula which is Kp is equal to Kc in the bracket of RT in the power of n. So how to get total n? So total n is the moles of gaseous product minus moles of gaseous reactant. So total n is equal to 2 minus in the bracket of 2 plus 1. So we get in total is negative 1. So Kp is already given in the question, which is 4 times 10 power of 4. So we're gonna times the R and T, which is 0.0821 times 700, and put the power of negative 1, which is the total n. So the RT, we got 57.47, and the Kp is 4 times 10 power of 4. So we're going to divide it by 57.47, and we get the Kp, which is 6.96 times 10 power of 2. So for example B, we're going to use a formula for case QC. So let's read the question first. Given the initial concentration SO2 is equal to 0.20 m, O2 is 0.10 m, and SO3 is 0.40 m. So to calculate Kc, we're going to use the formula where reactant divided by product. And at the same time, reactant has a power of coefficient and the product has a power of coefficient. So we put the value, we got 0.40 in the bracket of power of 2 divided by 0.20 power of 2 times 0.10. So after calculate, we got 0.16 divided by 0.004, and the total we got for QC is 40. So example C, which is direction of reaction, QC is equal to 40 and Kc is equal to 4 times 10 power of 4. So since Kc is smaller than Kc, the reaction will shift to the right to form more SO3. So that's all from me. Thank you for listening and watching.
Hi, and now I am going to show you how to use this equation. And the first thing you need to know what this equation means. And Kp is means equilibrium constant pressure, and Kc means equilibrium constant concentration. R is equal to 0.08206, and T is temperature, and delta n is difference in number of mole of gas. Next one, um, we need to know this is the important thing in this chapter. So as we know that Kc is equilibrium constant, and at the top of it we got Cd, in its numerator, and at the bottom we have denominator A and B. Right. So the next one, we go to next to the pressure and concentration. So as you can see here, PV is equal to nRT, while P is equal to N over volume R temperature. That means N over volume is concentration, and the P is equal to the gas times R and temperature. So the next one is simplify. You substitute into Kp. So you going like this. Kp is equal to C RT C B RTB over A RTA B RTB. This is Kp. So the next one, we need to recognize Kc and delta n. Kp is equal to Kc RT delta n, where delta n is C plus D minus A plus B. So the next one, this is for the example. The example is N2 plus 3H2, and we got 2NH3. If the Kc is 1.2 times 10 of power of 3, and the temperature we got 400 Kelvin. And this is how we done it. And we got here delta N is equal to 2 minus A plus 3, and is equal to negative 2. And Kp is equal to Kc. So as we can before, Kc is equal to 1.2 times 10 power of 3, and R, the formula of R is 0.08206, and time with temperature is 400 Kelvin, and don't forget the delta N. And we got here, after we after we times R with temperature, we got Kp is equal to 1.2 times 10 power of 3, 32.3, and delta N is negative 2. And we got the final answer is Kp is equal to 1.12. And that's all for me.
Hi, my name is Muhammad Makali, and my student ID is 20258530898. So today I'll be explaining about Chapter 6, Chemical Equilibrium, Le Chatelier's Principle. Let's go. What is Le Chatelier's Principle? If a system equilibrium experiences a change, the system will shift its equilibrium to try to compensate for the change. So next, Le Chatelier's Principle allows us to predict the effects of changes, such as constant, pressure, temperature, and catalyst. Next, the changing in concentrations only for gas and aqueous. Number 1, lower the concentration of remove some of the species. Number 2, the system will shift to produce more of that species. Number 3, increase the concentration or add some of the species. Number 4, the system will shift to produce less of that species. So next, if the concentration increases, the equilibrium shifts to the side that doesn't have X. And if the concentration decreases, the equilibrium shifts to the side that has X. Next, changing the volume or pressure only for gases. If the pressure is increased, the volume will decrease. The system will shift to the least number of gas molecules. If the pressure is decreased, the volume is increased. The system will shift to the highest number of gas molecules. Next, if pressure increases, the equilibrium shifts to the side that has less gas. If the pressure is decreased, the equilibrium shifts to the side that has more gas. Changing temperature. For every reversible reaction, if one direction is endothermic and the other is exothermic, for endothermic reaction, will absorb the heat from the surrounding. Increase temperature, then the reaction goes forward. Decrease temperature, then the reaction goes backwards. For exothermic reaction, it releases the heat to surrounding. If increases temperature, then the reaction goes backwards, and decrease temperature, the reaction goes forward. Next, using catalyst. A catalyst works by providing an alternative route with lower activation energy for forward and reverse reaction. Catalyst, it does not shift the position of an equilibrium system, does not change equilibrium constant, and only increase the rate of reaction. And next, factors that affecting equilibrium. Number 1, concentration. Increasing the concentration of reactants shifts the equilibrium towards product. Increasing the concentration of products shifts the equilibrium towards the reactants. Next, catalyst does not change the position of equilibrium. It only helps the system to reach equilibrium faster. Next, pressure or volume. For gaseous systems, increasing pressure will decrease the volume, and decreasing pressure shifts it to the side with more moles of gas. Last but not least, temperature. Increasing temperature favors the endothermic, and decreasing temperature favors the exothermic direction. And that's it. Thank you.